So here we have a circuit arrangement of a full bridge DC-DC converter. So this is the overall arrangement of a full bridge converter. And what is different than a simple DC converter? So the simple DC converter was using only one switch and an inductor. Now instead of one switch and inductor, we have many different switches, and instead of the inductor we have this as a high frequency transformer. So what will happen in this circuit? So let's say this is the positive of a DC supply and this is negative terminal of a DC supply. If switch number 1 and 2 are closed with the gate pulses applied to their gate terminal, then this winding is going to experience the current flowing from top to bottom in this direction. And similarly, if this is going to be the positive, this dotted terminals, according to the sign convention, they will be also positive, and they will also develop the EMF in their winding like this, and that will produce the voltage accordingly. So let's say positive and negative like this diode will be conducting, this diode will not conduct, and the output voltage will be rectified and the current will be smoothened by this inductor, and this capacitor will maintain the output voltage ripple to certain limit. Now what will happen if we turn on switch number 3 and 4 and turn off 1 and 2? So when you turn on 3 and 4, the direction of the current through the winding is actually opposite, and now instead of this diode will be conducting, and again what kind of current or what kind of voltage will be available in the output? That will be DC. So basically the full bridge converter is consisting of a full bridge inverter. So the input side is basically a full bridge inverter comprising of 4 switches which are turned on as opposite pair, and this full bridge inverter output is given to a transformer, and the transformer secondary is connected to a rectifier. So the rectification will be done in the output side of a transformer. Now this high frequency transformer can be a single or multiple winding. So there can be 1 winding or 2 winding or 3 winding depending on the design of the full bridge converter. So this full bridge converter will be very much useful in case of a high power converter along with a high ratio. So imagine a situation where you want to have 400 volt DC side and you want to get 48 volt output. So basically the step down ratio from 400 volt to 50 volt, this is approximately 50, where you have this ratio as 8. So 50 times 8 will be around 400. So 48 times 8 will be nearly 400, and you can see the ratio which we want to get is 8, and it cannot be handled by a single switch. So you can either use a multi-phase buck converter, or if the application is higher power, let's say high power, which means that greater than 500 watts or around 750 watts or and so on, then it is very much required to use the circuit arrangement similar to this. So here the stress of the devices are distributed among the 4. So whatever is the voltage blocking capacity of the device and the current carrying capacity of the devices, they are shared. This transformer helps in the turns ratio, and this turns ratio will decide about the input voltage and the output voltage. And it is also possible to have multiple winding, where one winding can generate 48 volt, the other winding can generate 12 volt in the output. But this 48 volt and the 12 volt generated from the same transformer secondary will not be called as isolated. So the 400 volt is isolated from 48 volt, 400 volt is isolated from 12 volt, but these two are not isolated from each other. And in some applications such as SMPS for a computer or a desktop computer, this type of power supplies are used. So the very fundamental requirement over here is the transformer secondary side diode are required to be very fast reverse recovery time. what will happen otherwise? So let's say if you are switching 1 and 2 and 3 and 4 combination of IGBTs at, let's say, 10 kilohertz, and this 10 kilohertz switching frequency will result into faster on and off of the current through this diodes. So if the diode currents are not coming zero at given period of time, then basically this reverse recovery of a diode may result into the failure. Less reverse recovery or faster reverse recovery time diodes are required, and sometimes in order to get it achieved in a better way, and because the on-state resistance of the diode are also very high, the synchronous rectification using the MOSFET is what preferred by designers. So this is the overall circuit arrangement of a full bridge converter, and let's try to understand this from power electronic expert in the Ansys. So how do I open the power electronic expert or PE expert? So I need to go to Simplorer, and from Simplorer I have an option from the twin builder window over here. So this is the twin builder option from the Simplorer, and here is where you can launch power electronic expert. So let us launch the PE expert and let's learn about the full bridge converter design. So I will go to twin builder and launch PE expert. So this is a template based tool as I have explained, and let's see what can be done. So I'm going to create a new design, and this tool can basically help us to develop a design based on the waveform or based on the converter. So let's say if I choose an inductor, what kind of design I can build? I can build a buck converter, boost converter, or buck boost converter. What if I'm going to choose an inductor? If I choose an inductor, I'm going to be asked for design of an inductor for my case. So you can actually design an inductor for your own application. So if you click on waveform based and click on OK, here is what you can do the design. So we can basically provide how much is what is the voltage waveform, what is the voltage level. Let's say our voltage level is 50 volt and we want to design this inductor, and we do not want the ripple to be, let's say, below some value, right? And the frequency is 200 kilohertz, then the value of the inductance will be 5 microhenry. So it's possible to have a continuous conduction mode with this case where average current is 2 ampere, the ripple is 20, and in order to reduce the ripple to, let's say, 1 ampere, this inductance value is going to become 100 microhenry, and you can actually define the inductance value, or you can define the duty cycle as well. So as I change the duty cycle, what you are able to see is this voltage and current waveforms are also changing. So if I change this duty cycle, you can imagine what is the maximum current, minimum current, how much is the ripple, and what is the average value. So here you can see as I increase the duty cycle, the ripple is increasing, and now in order to maintain that ripple to, let's say, 1 ampere, then we need to have a 230 microhenry of inductor. So now you can actually go ahead and design this type of inductor. So here we have 3 steps. One is waveform, one is design input, and another is the modeling option. So if I go to design input, I can choose all these options and I can basically go for modeling of this inductor, and I can figure out which inductor is going to be useful if I start the design process. So what I need to do as a next step is go to calculation and click on start design process. So let us start the design process for full bridge converter. So let me close this. So here we have a new file, and I'm going to now work upon a transformer based power converter where we have this options where we have a forward, classic, half bridge and full bridge. So let us select the full bridge. So I'm going to select the full bridge, and here the template of the full bridge will be available. So what you guys can see is the transformer over here and the input voltage, and the secondary of the transformer over here in the output, and you can fundamentally see the waveform as well. So if I change the duty cycle, you can see what will happen in the output voltage and the current. So you can choose to see the current in the secondary side or the primary side. So let's start our design, where we have the input voltage as 48 volt and the output voltage as 400 volt. So this is our voltage requirement, and let's say we want to design this for 5 kilowatt. So 5000 is watt is the design, and here is what you can see the current on the output side, which is 400 times 12.5 will be 5000 watt. Now you can define the current ripple, and you can actually choose the ratio of the winding turns as well, and this winding turns ratio can be chosen from primary or secondary. I can select the waveform from here, which waveform you want to see, primary and the secondary. Only the levels will be different, and if you want to see this currents, you can see the primary winding is 48 volt side. You can see the maximum voltage is around 50 volt, and the current at the same time is 200 amperes. So for 5 kilowatt and 50 volt, this is going to be the level of the current. So the peak value of the current will reach to 200 amps, and we can actually decide the current for this case. So the average current will be again be dependent on the duty cycle, and you can see the waveform on the primary side and the secondary side. So the secondary side is 400 volt side, and because of the inductance of the transformer, the highest voltage that switches are going to experience, that is 1000 volt, right? So this is about the fundamental step. Now let's go to the design inputs, and over design input you can actually choose how much is the spacing for the winding, how much is the ratio for this, whether you want to consider the thermal consideration or not, whether what is the variation in the turns ratio which is allowed, how much is the maximum flux density versus saturated flux density ratio. You can see the limiting value of the temperature. You can see select the winding setup, and there are so many other things. So whether you want to select the Ansys iSpec, basically the Ansys iSpec is for temperature and the flow simulation, and you can choose the natural or force or any type of simulation from here. So if you do this, then there will be certain modeling options over here, and before we actually do the design process, let us save this model. So I'm going to save this model in the project files, and let me create a new folder. Let's say design 1, and I'm going to save this full bridge file. So now once you have saved this, you will be able to start the design process from the shortcut available over here, or you can go to calculation and select start design process. Once I click on start design process, here is an error coming up. Let's see what is this error. This is related to no design library selected. Let's understand what is a design library. So what you see over here is a design library, and these are the material available in stock for your case. So these are the stock libraries, and here you have AVX cores, EPCOS cores. These are basically the companies who are manufacturing this cores. So here you have bobbin, wire and material. So all those libraries required for designing of this transformer are added over here. So what we need to do, we need to basically add this library into our design library. So if I add this, now I have an EPCOS design library where I have EI type of core and let's say EE type of core. Let's see one of the EI type of core. So this is the arrangement for EI type of a transformer, and if you can see those dimensions, all this core and the dimensions are mentioned over here, and these are the actually commercially available core materials, and you will be able to see the material related to bobbin, wire as well. And go to wire, you have these 4 options: foil, lids, round and the square, which are popular for design of the high frequency transformer. So the entire template is going to work upon the high frequency transformer selection and its analysis. So all other analysis can be done quickly in case of a circuit simulator, but this is going to give us an idea about the magnetics of a high frequency transformer. So let us go ahead and select the start design process. So if I click on start design process, it is going to ask me that there are no cores selected. So what I can do manually selection of my core material and bobbin and wire. Otherwise this tool can automatically assign for us. So I will click yes over here, and the same is true for the wires and materials, and it is going to choose the competent material for us. So what is the output of this exercise is we have got 162 valid design from 1539 designs, and the top 10 designs are selected over here. So now we can see in the output, after this modeling options, we have the constructive results, performance results and list of results. All these 3 tabs added over here. So I can choose the constructive result. Here is where we can actually see the transformer magnetics, and we can see what is the core size, and say for this design PM62/49 is the core selected for this case, and here are the dimensions in the millimeter. You can convert it into inch as well. So this is the transformer design which is there, and it has a multiple number of winding. As you can see, the cross section area are also changing over here, and you can see the type of the wire and their standard wire gauge number. So this is also available in the tool. What can be done in case of a performance result is you can see what are the total losses inside a high frequency transformer. So for a high frequency transformer, there is a core and a winding. So the winding filling factor, the winding rate and the losses are explained over here. The magnetizing current is shown like this. So this is the value of the magnetizing current for our application, and you can see all other parameters like how much are the total losses. So for example, I have input 5000 watts, and for those calculation we have total loss of around 21 watts, and with whatever input we have given. And you can see the window occupancy percentage, the flux density value in millitesla, the highest temperature is 100 degrees centigrade, and so on. This is based on the material property available in the tool. So here we have a list of results, and for which we can choose any, and then we can move ahead with modeling with either Maxwell 2D or the power electronic magnetic tool. So what is the next step after doing this? We need to select the modeler over here, and from modeler you can select the generate model. So when you select the generate model, you will be actually able to translate your design into Maxwell 2D or any other options. It is also possible to translate your design into Twin Builder or PSpice or Sabre, which are other than Ansys tools. So let's click on generate model, and I'm going to select the default option over here. I'm going to open this model with PE Expert, and PE Expert modeler is PE Magnetics, and optionally I can generate finite element analysis 2D based or 3D based with considering capacitive effect or without considering capacitive effect. So let me click OK with the PE Mag option, where it's a power electronic magnetics option, and when I do so, I'm going to now open this design in PE Mag tool. So this is a PE Mag tool, and this is the overall arrangement of the transformer winding. So what you are able to see over here is the transformer design done in PE Mag. So here we have this coil, here we have this insulator. So all these green colors are insulators, all these are winding, and all these windings and insulators together will be connected to the terminals. So here we have AA, BB and CC as a pair of 3 terminals. So this is going to be the transformer design, and if we see the winding arrangement, that is also possible to be seen from here. So this is the winding arrangement done, and this is a cross-sectional view of that winding arrangement and how you need to isolate one winding from another winding. And so when you have let's say this group of conductors in yellow color and this group of conductor in red, you need to provide the insulation material as well, and that is taken care by this design. So here what you have is the current design, where it's a core, bobbin and a winding, and you have a design status. And from here what you can do, you can call 2D modeler, 3D modeler, or you can go to eddy current analysis, you can go to FEA electrostatics and so on. So this is the PE Mag model available over here, and you can analyze the results. You can transport this model to any other tool. So this is about template based design using PE Expert and PE Mag. So we created a full bridge DC-DC converter, and we analyzed that how Ansys tool will select the components from the available library and how it is suggesting us. What if you do not have any readily available component or any off the shelf component? Well, that is the case with most of the power converter. So the resistor, capacitors and other components like diode and switches, they are available off the shelf, or we just have to choose them. But when it comes to magnetics, you have to design them. So the power converter engineers will have the magnetic design exercise using inductor design and the transformer design, and this tool is going to be very effective for new design of a transformer or an inductor for a power converter. So these are the templates, and over here you can create your own component of transformer or inductor as well. So now let me close this, and let us now go back to PE Expert, and what you will be able to see as the values of transformer chosen, and you can actually have the core material properties, and you can see over here additional parameters. You can find out the core losses. This is based on the data sheet of a transformer, and you can see the BH curve as well. So these are the BH curve for both the cases, and here you can see what are the electrical properties of this material, and you can see most of the things related to core. An N87 type of core is actually commercially available type of a core. So if we see this type of our core design and dimension, we can actually verify them with a core material and the core commercially available cores. So if you can search for PM62x49 type of a core, you will be able to find this type of core, and you can actually start your first step of hardware design with this type of a core. Now along with the core, you need to figure out a compatible bobbin. This is possible to include over here. So this is the end of demonstration with PE Expert. Let me close this now. And now let's say we are back to Simplorer, and basically in Simplorer, as I explained, you can drag and drop all the components and create your circuit.